Hi guys, welcome to my YouTube channel Study with me. In this video, I'm going to talk about band pass filters. Not only that, we are going to simulate it. Amazing. Now, let's see what is the circuit arrangement for passive band pass filter. Here is the input voltage source and here is the inductor. Here is the capacitor and last we have the resistor. The important thing is the output terminal voltage is taken out to the resistor. Now the big question is why this circuit is identified as a band pass filter. Don't worry, here is the answer right in front of your eyes. First of all, you know that the impedance of the inductor is given by L into omega, and for the resistor it is just R, and for the capacitor it is 1 over C into omega. Now just think omega is increasing along the x-axis, so we can see L omega can capture higher values and 1 over C omega can capture lower values, and the resistor will capture the middle value. So I think you can understand the sense why this circuit is called as a band pass filter. It's just for the understanding. It is not an standard thing. Okay. The most important part of any filter is the transfer function. So here also we can obtain it by dividing V output by V input. Here the transfer function is in Laplace domain. That is because it is kind of a standard thing and it makes the calculations easy. Anyway, we can get the transfer function in algebraic form in this way. The output voltage equals R over Ls plus 1 over Cs plus R into Vin, which is the input voltage. So we can divide V input into the left hand side and get V output over V input equals Hs, which is the transfer function in the Laplace domain, equals RCS over CLS squared plus 1 plus RCS. After that, we can rearrange the transfer function into this form. Okay? And the important things to note here is the coefficient of the S squared is 1. And here you can see 1 over Ls. This is just the squared of the center frequency, which is omega naught. And here you can see R over L. It is just the bandwidth of the band pass filter. And both of these terms will come along shortly. So don't worry, just relax. Now we have to convert the transfer function into the frequency domain, and you will see why is that shortly. So just wait. Anyway, for the conversion we have to replace S, which is the Laplace operator, with j omega. Here omega is the frequency of the input waveform, and we can receive h of j omega as this, and we can reform this as this, and you can see h of j omega is just a complex number with denominator and numerator. So just observe the real and imaginary parts of the denominator and the numerator. Okay, let's go now. Now we are going to see why we did that conversion. You happy? Anyway, however, we can take the magnitude of the transfer function just considering it as a normal complex number, and then we can take the phase angle of the transfer function in the same way, considering it as a normal complex number. So study these formulas and figure out how these formulas come into existence. I'm sure you are able to do that. So now we are going to see how the magnitude of the transfer function and the phase angle of the transfer function is varying with the angular frequency omega. To do that, we are incorporating two formula, which is the magnitude of the transfer function and the phase angle of the transfer function. And now you can see the two plots. Now we are going to look into some kind of deep manner into the magnitude plot of the transfer function. Okay, right. Here you can see omega naught. Omega naught is called as the center frequency, and here omega C1, and here you can see omega C2. These two frequencies omega C1 and omega C2 are called as cutoff frequencies. Okay, and the range of frequencies falls within these cutoff frequencies omega C1 and omega C2 are called as the bandwidth of the filter. We indicate it as beta. Okay, then note that the magnitude of the transfer function when omega equals omega naught is 1. It is defined as that. Okay, then when omega equals cutoff frequencies, you can see the magnitude of the transfer function is 1 over root 2. It is also a definition. Another important thing that we can observe in the magnitude plot is when omega frequency is lying out of this bandwidth, the magnitude of the transfer function is decreasing rapidly, which implies the attenuation is comparatively high when omega leaves that range. Okay, then we can only get a less attenuated output voltage waveform only when omega stays in that range. So it is why it is called as a band pass filter. Right? Okay. Next we have the phase angle plot of the transfer function. In this also, when omega is out of the bandwidth of the filter, there is a significant phase shift of the output voltage waveform compared with the input waveform. So, finally we can see when the input frequency doesn't exist in the bandwidth of the filter, the output voltage waveform will not only get significantly attenuated but also phase shifted. So now let me introduce to you three guys. Actually, I mentioned about them previously. Okay, so the first guy is the center frequency, then the cutoff frequencies, and at last the bandwidth. As you can see, the center frequency is omega naught. More clearly, it is the frequency that the magnitude of the transfer function is maximum. Unless we can say the magnitude of the transfer function is 1. Okay, anyway, we can come up with the center frequency, a value for the center frequency by this formula. Okay, so look into previous slides and you will find how I came up with this equation. So by this equation we will find omega naught equals 1 over square root of LC. Okay, now we have cutoff frequencies. The cutoff frequencies are defined as the magnitude of the transfer function equals 1 over root 2. So depending on that, we can establish this equation. Then by rearranging it, we can come into this equation, right? Then we can reform it as this, and finally we can arrive into this quadratic equation of omega c. Here omega c means the cutoff frequencies. Okay, actually in this equation omega c equals plus or minus r over 2 into L, again plus or minus the square root of this. However, here we have 4 values for same omega c, but in this scenario only 2 values are applicable. Actually speaking, we want only positive values because cutoff frequencies are always positive. So depending on that information, we can decide what values that we should be selecting. So note that the greater part is the second part here. So depending on that information, we can decide what are the cutoff frequencies. So omega c1 as this and omega c2 as this. So here are your cutoff frequencies. Now here is a trick. We can check whether the cutoff frequencies we found are right or wrong. You just have to do the multiplication of the two cutoff frequencies and get the square root of them. And if you arrive into the center frequency, your cutoff frequencies are right. You can test it with an example. Okay. Now here we are with the bandwidth, and I am pretty sure you remember the beta from the magnitude plot of the transfer function. Okay. So here bandwidth is beta. So we can obtain the bandwidth by getting the difference of two cutoff frequencies, and we can arrive into the equation beta equals R over L. It is just a small fact, but hold on to it tightly because it is important. Now here is the quality factor. We can obtain the quality factor by dividing center frequency by bandwidth, and doing some kind of maths, we can arrive into the ultimate equation Q equals 1 over R into square root of L over C. Here at last you have a little challenge. See if you can derive these equations for cutoff frequencies omega c1 and omega c2. Now we are at the interesting part. Here we are going to simulate this bandpass filter in the LTSpice software. But before that, I want to highlight some important points. So here we go. I have assigned some some numeric values for the inductor, for capacitor and resistor. So depending on them, I have arrived into the cutoff frequency, center frequency as this, and for cutoff frequencies as this, and I have graphically illustrated this bandwidth like this. So now you can see the simulation. First of all, here we are going with omega 1. Here you can see the original waveform in green and the output waveform in blue, but here you can't see the green waveform as it is under the blue waveform. Then we are going with omega 2. Here you can slightly see the green waveform, and omega 2 is within the bandwidth of the filter. So the attenuation is less. Now we are going with omega 3. Here you can see a considerable large attenuation in the output voltage waveform, which is in blue. Now we are going with omega 4. Here also you can see a slight attenuation because omega 4 is in the bandwidth of the bandpass filter. Now we are going with omega 5, and the attenuation is a much higher one, because the omega 5 lies out of the bandwidth.